My name is Kristina Kermanshahche, and kudos to Jason for pronouncing it. And I'm really privileged to be here. I really wanted to first thank George and DDN and Intel, and especially to Rockefeller University for hosting us. I have just recently founded a new company called Perspicace, and we'll talk about that in a minute. But I'm going to be talking to you about high content screening and drug discovery as an example in the industry. So Perspicace, you can think of us as everything HPC and AI. It spans everything from running benchmarks and helping scientists scale really innovative pipelines into a production scale throughput to keep pace with the high throughput instruments that we've been talking about. It's solution architecture, it's applied machine learning. In many ways, it's taking all of the great developments in cryo-EM and in genomics and other areas and really applying it for everybody else. We're strong supporters of open source. Anything that we develop we'll be publishing and making that available to the community. And I think the example today will give you kind of a good sense for our approach. One of the things that we definitely do, and you'll hear me mentioning quite a bit, is we really start from wherever your challenges are. Been working for a number of years with scientists from around the world. We always start very much like today. What are the challenges? What's holding your science back? And then we'll put together solutions with you and then teach you how to do it for yourself. So I always like to start with the end results first, so you kind of know what we're talking about. I'm going to talk about a great collaboration, a scientific collaboration between Novartis and Intel that's been significant over the last couple of years. And the latest result, the work is ongoing, the latest result is that we were able to deliver a 20x improvement in the faster time to train. I'll go a little bit more into the details on the science about what is high content screening and why is it important to drug discovery. But we were processing a 10,000 image data set, and we reduced the training time from 11 hours to just about 31 minutes with 99% accuracy. So how do we do that, and what was the significance of it is what we'll talk about today. So first I wanted to go through the acknowledgements. It's a fantastic team on both sides. I'm talking about it today because I was, at that time, I was Chief Architect for Health and Life Sciences at Intel, and I spearheaded the project in the collaboration between the Novartis team. And the Novartis team, it was a great example of close collaboration between the HPC technologists and the data scientists working between Cambridge and Basel, Switzerland. So here's a typical high content screening environment. Looks probably familiar to you because you could probably draw a similar diagram with cryo-EM and many of the other high content screening or imaging scenarios. The thing that I wanted to draw your attention to was you can think of it as, I guess, simply as three different areas. There's the ongoing iteration and work going on in the wet lab area where you're constantly experimenting with reagents, looking at protocols, and developing new assays. Again, also, as a number of you are here, you're also constantly trying to improve the hardware and image acquisition protocols. And then I'm going to be talking more about the image and data analysis, but it's always important to think of it as a holistic problem domain. Whatever advances we can do with the image analysis, trying to keep up with the high pace of the instruments, you're really trying to enable the science that's going on in the wet lab. And how do we get faster results? One of the key challenges that the scientists described to us was the fact that if it takes essentially forever to develop the images and to process the analysis, it means much less experimentation that can go on. It's a rate limiting step to discovering new compounds and screening them and bringing them to market. So the whole point of this is you really need to keep in mind, even if you're focused with a team and you're specialized in one particular area, you have to constantly look at the other areas and make sure that you're not missing something. So how much data do we have? Well, opinions are divided, but it's a lot. This is actually an older example using 96 wells in a well plate. You might get 1,400 cells per row. That might be 17,000 cells for a given plate. But the reality is, now it's more typical that you're using a well with a plate with 384 wells, or 1536. The reality is a typical high content screening experiment might use 1,000 to 1,000,000 compounds. So that means many plates. And really the opportunity here is if you can advance all three areas, you can significantly change what you're able to measure. So that just kind of gives you a little bit of a view. I like the picture kind of gives you a little bit more perspective on, another thing I'm going to talk about in a minute was typically scientists are taking the view of the image and tiling it, and so that was one of the big challenges. I kept hearing scientists were essentially designing their experiments around these small images. So let's talk about I'll talk about that in a second. So one of the key things that the Novartis team had started to do was they took a look at the literature, that's where we all start, and looked at a conventional high content screening analysis pipeline, which is shown on the up above. And very much like some of the other discussions here, in fact, if you've seen videos on autonomous driving, you're probably all familiar with the little, drawing the bounding boxes around the image, trying to do the object detection, feature extraction, selection, and then eventually into classifying the phenotype. In this case, what you're looking for is the phenotypic expression of the compound that's been applied. Are you enhancing growth, or are you restricting growth, for example? How can you quickly go through the analysis and find the compound of interest? I think there's a direct parallel here with the earlier developments in speech recognition and natural language processing as well, where people would heavily engineer their pipelines and essentially break all of the different steps, very much like is pictured here. In speech recognition, they would take an audio sequence and break it down into the phonemes in order to recognize the recording. But what we found with deep learning and the advent of more technology and much, much more data is that these things are uncannily able to figure it out for themselves. We don't need to go in and engineer it ourselves. So the Novartis team had started to use something called a multiscale convolutional neural network without all of the individual steps, and was able to get much higher accuracy. And importantly, you're able to more readily generalize the network. You're not trying to develop an MCNN for one particular experiment. That's really not very scalable, right? You really want to create a deep learning model that you can then apply to multiple experiments. And going back to the lab picture, think about the fact that as you're doing one of these experiments, you're constantly experimenting with and tuning and optimizing the fluorescent stains, for example, or you're playing with the compound concentration. So if your focus is there on the science, as well it should be, you don't want to have to keep rebuilding models in order to satisfy the next experiment. So how do we make this go much faster in order to enable the science? You've all heard of the ImageNet examples that are widely promoted in the industry. If you think about the typical images there, they're typically 224 by 224 pixels and then 3 channels for RGB. So if you take your favorite cat picture, that would be the size that's processed in the ImageNet. High content screening is much larger. It would be like taking that cat picture and multiplying it by 26. And in fact, if the actual goal is to do whole slide images, it would probably be double of that still. So here's a comparable example of a high content cellular image, much larger. So during the discussions with Novartis as we were starting this project, we talked about posing a grand challenge. Again, what's holding the science back? What would you do if you could? And ideally, they would use a whole slide image, essentially. You would look at not just individual cells or subcells, which is what the focus has been previously, but you'd actually step much earlier into the process and actually look at the entire population in the whole slide image, or the given well. So the grand challenge that they posed for us was, can I process whole slide images? It's something about 5 megapixels each. And can I do, let's say, 100,000 in a day? Because that would dramatically change the drug discovery pipeline for everybody. Okay, so I'll quickly go through some of the machine learning optimization strategy and the best practices. Because it's not a data science conference, I'll play a light touch, but there's plenty of articles that go through the approach that we can go into more detail later. The first thing is adopt the latest optimized frameworks and libraries. Use the people who have software optimization and programming as expertise. That frees you up to focus on your science. I was a strong proponent for optimizing Python, for example, letting scientists to work in the language of choice, and then providing near native performance without having to reverse engineer your code. The other perhaps minor point, use containers to manage the software dependencies, which can be horrendous. You probably know about Docker, you may not know about Singularity. Use something. Singularity was designed for HPC workloads, so it's much more performant, and it was built with security from the ground up. So it's a little bit more suited for these types of analytics. So the next phase would be maximize your performance on a single node, where you can control everything and get as much performance as possible. When we started, Novartis was using Caffe, and Caffe is a great framework, but it wasn't quite as performant as TensorFlow. So partway through, we switched over to TensorFlow, and these all go in iterations. So I would say, if we went back now and tried Caffe with some of the key learnings that I'm about to go through, I suspect that they would be on par. But at the time, there was a significant difference in the way that the two frameworks were parallelized. So another error that we really had to overcome, you go through your hyperparameter tuning, including the batch size and learning rate, and there's a lot of experimentation to get it right. One thing that's really important is to monitor your accuracy and your gradients to ensure convergence. We had, any of these projects, you're bringing together a lot of different experts. You may have your data scientist, you may have a software engineer, you may have a performance expert, and you hopefully have the scientific experts to fall back on to make sure that you're not going astray. It's very easy to lose sight, so that we found you can lose weeks or months at a time, and perhaps you're only looking at performance and you've completely lost sight of the fact that your model isn't converging. That sounds ridiculous, but it actually happens. So these are written down because they were hard lessons to learn. One of the key things that we learned earlier this year was this concept of scaling multiple workers. I've got some more slides that will go into that a little bit. Normally, I think I'll have the slides catch up. So this is a quick example of a multiscale convolutional neural network. Why is it multiscale? Because if you look at it vertically, we were processing whole slide images at the top, and then we were reducing the resolution as we went down, so we could capture simultaneously or in parallel different, from fine grain to coarse grain features. And then because of the improved parallelism of TensorFlow, we were able to look at and learn multiple features at once. And one thing to point out, again, a factor of the image size that we were working with, the model size was pretty significant. So we were constantly monitoring how much memory we were using, et cetera. So it's really typical that you run, the default behavior would be you'd run one model on one node. On most machines, let's say it's a two-socket system, that's actually two processors. This is probably way more detail than your scientists ever want to know, right? One of the things that we discovered, and it wasn't just us, it was a number of papers in the industry, they started to figure out that, wait, if you ran 4 models on a single node, you would dramatically improve the performance. The great news about this is it's a simple config change at runtime. There's no code or framework changes required. So this is a best practice that really we need to disseminate. So on training, we figured out for this particular model that 4 workers per node worked the best. You'll see some benchmarks out there that show on inference we were able to do 8. So you have to, that's one of the things you have to tune and play with, but this was a key learning. The combination of this and some changes that we made to the learning rate were significant. Again, we had a model for months, I won't say how long, for months that actually wouldn't converge. We had tremendous problems, and we had, you know, brilliant people on all sides trying to figure this out, and it really was, you know, constantly polling the community and talking to people and figuring out and trying different things. So this sounds simple now, but it was actually a huge breakthrough. And on the single node, I've condensed all the material, so there's benchmarks, so I'm just not showing them. On a single node going from 1 to 4 workers, it was about a 2.2x speed up. So that was a huge performance gain right there. So now, after you've got you know, as much performance or making use of available infrastructure on a single node, then you switch to working with multiple nodes. And how do you, you know, span these models across a cluster, with the idea that if you can get really good scalability, then you can process larger and larger images and get towards that grand challenge of 100,000 images a day. So if you're scaling across multiple nodes, you need to, again, really look at the fact that you've got a balanced, or, you know, do you have a balanced cluster infrastructure? You suddenly care about what fabric you're using. You care about the storage. You'll start to encounter significant I/O issues if you're not paying attention. In order to do this, we used Uber's Horovod and MPI in order to synchronize the gradients. There's more developments underway. There's Intel, for example, has another library called Machine Learning Scalability Library, MLSL. It's already integrated into Caffe. They're working to integrate it into TensorFlow. So for right now, use Horovod. There's a paper that's linked later you can get the details on. And then you have to adjust the learning rate to achieve conversions. So again, this was something that there's been a lot of active research. These are things that change on sometimes a weekly basis. So you need a team just to go out and read all the papers as they're published to keep up. The chart on the left shows kind of the established scaling rule that you have an exponential decay as you proceed through your training epochs. What worked for us, so you have a concept of a warm-up period, not unlike running a typical workload benchmark. You typically want it to warm up and get to full capacity before you actually take the measurements. So I find an interesting parallel there with machine learning. So you have a warm-up period, and then you scale the learning rate according to, as a factor of the global batch size. And then you have an aggressive decay. Without these changes, we could not get the model to converge. But with these changes, it was night and day. So I think we talked about before about kind of learning what are the essential things to tweak and what are the things that you can perturb with a fair amount of reliability. So we're happy to say that we were able to get state-of-the-art accuracy on eight nodes with a global batch size of 256. So the individual performance gain, with everything held constant, going from 1 to 8 nodes was 6.6x. Again, the end result from where we started, maybe more than a year before that, was about 21.7x performance improvement. And then it also shows kind of the memory used Essentially, the way to think of this is, you can process significantly larger or more scientifically realistic workloads by scaling out over a cluster. So now I'm going to just wrap up briefly and talk about. Remember, I said it's really important to think about how do you process heterogeneous compute and how do you ensure that you're actually working on a balanced compute infrastructure. It's not just the processor type, it's not just the framework or the model. It's really putting all of those things together to come up with the results. Very quickly, the chart on the left is an interesting. Facebook did an analysis of their peak usage of their data center, and obviously, like many of us, just not on their scale, they were seeing dramatic changes in their workload utilization throughout the day. And the reason why I'm showing this slide is just it's never about a single benchmark on a single workload on a single node. That's not reality. Reality is you've got lots of different users trying to use a shared cluster. You've got to be able to account for that. So that's important when you're doing benchmarks that you're actually factoring that in. So always taking a realistic set of users and how they need to work with the technologies. On the right, upper right, an eye chart, is Facebook, as part of the same paper, was taking a look at, well, here's the different types of workloads, and actually, as one would expect, use the right technology that delivers the right results. So some of them are better on CPU, some of them are better on GPU. The reality is you need to support lots of different workloads, and you'll need to provide both. The chart in the middle is just, I think, more humor than anything else. All of the cloud vendors, as it was getting close to the NIPS paper deadline, NIPS is one of the top academic machine learning conferences. So the deadline was getting near to all the scientists were running their workloads, trying to get the papers in, and everybody's capacity was tapped. The spot pricing went through the roof. Not probably much different from what happens on your local clusters from time to time. As I said before, you want to use the technologies that do the best job. You also want to make sure that you've got capacity for your users. The way you do that is to, we're in a heterogeneous compute environment, so maximize whatever that you do have so that it's there for you. I've got two slides that talk about the importance of DDN and having a parallel architecture. This is a classic example. This is actually a deep learning example, but I could show you the same kind of slide for genomics or many of the other computationally intense pipelines, where showing kind of night and day difference between running off of NFS versus running off of a shared parallel architecture. In this case, it's comparing what you want is full GPU saturation. So the green line at the top is a good thing. It means that you're constantly feeding the GPUs and maximizing the use of that capability. What we did in that case was we were prefetching and pulling the data into memory so that the models could be running efficiently. Down below, it shows the alternative. What you don't want to see happen is, again, like rate limiting step. If you're constantly trying to get the data off of NFS, you're fighting I/O bottlenecks right and left. And it's actually one of those. It's a good example where if you're using a single connection, NFS may look fine, but you won't see it until you start to get multiple users or multiple jobs. Making demands of the cluster at the same time, and then you see a huge delta. So down below, you're seeing GPU starvation, and you're holding up the whole cluster, and you're wondering why none of the jobs are finishing. Another example, again, a nod to the fact that you need to pay attention to your whole workflow. In this case, a lot of machine learning is really around the data preprocessing and the preparation. So in this case, DDN converted a lot of the individual files, could be individual image files, converted it into a TensorFlow TF record because it's much more efficient way of streaming the data and keeping the processors fully committed. So on the conversion benchmark, it was running 3x faster. And then in the classic ResNet 50 training example, because it was running TF records off of the DDN storage, it was running 2.5x faster. So again, just important to look at your overall architecture and making sure that you're don't just look at performance. You got to look at accuracy. You need to look at I/O and memory. Look at the complete picture. So just in closing, the website will be up in a couple days, so be patient and stay tuned. You'll find a lot of examples of work that we've done around the industry. Again, just really, really blessed to be working with a lot of great industry experts like yourselves. Since a lot of the discussion today is about cryo-EM, I just want to make a big pitch that finally, after waiting forever, we've got the Reliant 3.0 paper published, so very eager to hear what you guys think. I know some of you have been working with it beforehand. Engage us with a grand challenge, and let's see what we can discover together.
Maybe before we go to questions on this, I just want to quick poll the audience. So I know the speakers today, I think everybody's mentioned machine learning in some aspect or another for analysis. Of everybody here, who is either currently involved in doing machine learning or currently involved in supporting people who are doing machine learning? All right, and now you can keep your hands up, but of the rest of you, how many expect that you will be in the next year? Is that also, yeah, okay, so pretty much everybody, this is spot on for you guys for thinking about, the best practices Kristina talked about, for how to do this right as you're going through the learning curve. I found that, very useful, and I jotted down a lot of notes on that because, I think everybody learns a lot of these same lessons as they go through. So what you can take away as a best practice is great. Questions for Kristina?
I'm Mark Bruce from Microevolution. With your high throughput screening work, is anybody doing things in 3D yet, or is everybody still just working in flat 2D samples and getting by?
I'm not the scientific expert on that, but I think they're still primarily working in 2D. But if I go back to the screen that talks about all the different types of data, right now there's more data that's available than we're actually making use of. And all areas of imaging, we can say that. Cryo, I've worked with some of the Harvard Medical School folks, different from what was presented here, on a different area of brain imaging. You think about all the MRI data, radiologists can't make sense of that, and yet if we unleash statistical processing on it, amazing what we can start to uncover. So I think, and in that area, for example, they're doing 3D significantly. So I think it just probably varies between the different modalities.
Adding to that, in almost more direct response to your question too, at least some imagers can do multi-Z level scanning within a well. So it is possible to do 3D. I don't know how widely used that is, but conceptually.
So I do have one question, or ask your experience. In your talk, it was a very, say, benchmark heavy talk. And nothing makes me happier. But one of the things I find working with scientists is that their tolerance for benchmarking is maybe not quite so high.
No.
The postdoc is, my run is done, and now I'm going to go on and do something else. And why are you asking me to do it 10 more times with different parameters to get the same answer and so on? So I guess
because the answer is different.
Well,
every time you run it.
If the answer is different, that's maybe cause for concern in some cases. But I guess where do you find that the actual payoff is, and then where do you find that the ability to engage with with researchers who may not necessarily care about maximizing efficiency begins and ends?
Well, I always think of it as if you think of the realm of early R&D to doing production scale, could be in manufacturing or in clinical operations or what have you, right? At the early stages, a scientist who's developing a new algorithm, they should write in any language they want. They should just get the job done. It's typically not, you don't care about performance until it's holding you back. And so if I think about the work that we did with the Broad Institute on GATK, for example, top scientists writing industry-leading algorithms, they don't care if there's a performance issue until they're actually scaling to meet the latest sequencer. And then you suddenly care. Or if you're trying to make it reproducible and go into like an FDA clinical trial or whatnot. So I think it just depends. I think and even the I think we're all going through this, transition together. When we think about, if you go back, I don't know, 5 years ago or maybe even more recent, it was the postdocs who were going through and manually annotating all of those images. Okay, until if you don't realize that something could be different, you don't realize that, so it takes 3 to 6 months to go in, and I'm going to switch to cryo-EM for a second. It takes 3 to 6 months to analyze my cryo-EM data. And it's extremely scarce time to actually book time on the microscope. And if you don't find out for 6 months that your experiment was screwed up, that's a problem. So, all of a sudden in the last year or so, we've dramatically changed how quickly we could do that analysis. And now we're all talking about, wouldn't it be nice if we could start to do real-time imaging? Well, that would be fabulous. And, we're talking about a couple of different modalities here. Why can't we do that across all of them? So it's exciting times.
If there are no other questions, I think given where we are in the schedule and the fact that we had a canceled speaker after lunch, I think now might be a good time to break for lunch, and we'll come back for the panel and pick up there. Okay, the lunch is
Thank you.